Welcome to Chapter 13. The first several exercises of this chapter are focused on implementing the Riemann sum as an approximation of the definite integral and showing that as the Riemann sum increases its resolution, so as we have more rectangles to estimate the area under a curve, then our approximation gets better and better, and eventually we will reach the exact analytic solution to integration. But more on that in later exercises. For now, in exercise 1, the goal is to calculate the breakpoints for segmenting a function into a small number of bins for Riemann sum calculations. So in particular, what you want to do is calculate delta x and then the breakpoints for the following parameters. A, this will be the left or the lower bound. A is minus 0.5. B, which is the upper bound, is pi, and n is 14. So we want to have 14 segments between minus 0.5 and pi. Now, I haven't yet told you the function we are going to work with, but that doesn't matter. We don't need to know the mathematical function to integrate before calculating delta x and the breakpoints. Okay, so once you have these parameters, then you define the partition breakpoints twice. One as a direct implementation of equation 3. I will scroll up to that in a moment. And for this, use list comprehension. And then again, a second time, calculate all the partition breakpoints, the boundaries of all the little segments, using linspace, the linspace function in NumPy, to get n linearly spaced numbers between a and b in order to create n partitions. Okay, and then basically what you want to demonstrate is that these two methods give identical results. So we can print out here the delta x that's based on the formula. I'll show that in a moment. And then here is the distance between successive partition x values. Now those should be the same according to the formula. And so if they're not, then, either you've used linspace incorrectly or you've implemented equation 3 incorrectly. Okay, and then you want to show the breakpoints from the two methods, list comprehension and numpy.linspace. Now, both of these breakpoints should be exactly the same. I've just cropped out a few in the middle here just for, to make it look a little bit nicer in the book text. Okay, and basically, the goal of this exercise is just to make sure you really understand the concept and implementation of segmenting a function into a small number of segments for approximating areas. Here are the two functions that we are going to be applying or translating into Python code. So we have this equation 13.2. Here we say that delta x equals b minus a divided by n. And then the next equation is this one here. So this is defining all of the x-axis breakpoints for segmenting the function into intervals. And this is what you want to implement using list comprehension. Here I am defining the integration bounds, a and b. Here I'm creating delta x. So yeah, very simple, b minus a divided by n, where n is 14. And then here is the two methods for defining the partition points, all the points that break up the x-axis into a small number of segments. Here is with list comprehension, and this is literally just an implementation of the math. This was equation 3. This was equation 2. And then I'm using linspace to get n plus 1 numbers between a and b. And remember, we need to have n plus 1 here and here, because the n is specifying the number of intervals that's here. This is the number of intervals. And if we want 14 segments or little intervals, we need to have 15 breakpoints to define them. So you always need n plus 1 partition points for n segments. Okay, and then, the rest of this exercise is just printing these out. So here I have delta x calculated directly by implementing equation 3. And then I have the distance between the x-axis points, and that comes from the output of numpy.linspace. And here you see, these numbers are the same, and these two lists are the same. Here we are with exercise 2. We are not yet at the point where we are going to estimate areas and calculate definite integrals. In this exercise, we are basically just going to do some visualization, and that's going to set us up for the approximations and basically the calculus in the next couple of exercises. Okay, so here is the key function that we are going to work with. F of x equals e to the x divided by 10 plus the cosine of x. So translate this mathematical function into a Python function that takes x values as inputs and provides y values as outputs. So that part is fairly straightforward. Just write a Python function to implement this or to evaluate this math function. And then you want to create this graph here. So what are we looking at here? Well, here we have the function shown in the black line here. This line, this vertical dashed line and this vertical dotted line over to the right, this shows the boundaries of integration. This is the lower bound of integration and the upper bound of integration. And then I've drawn as a patch, as a light gray patch, the area that we want to calculate. Okay, so this is the area under the curve that we want to know. In the next several exercises, we're going to estimate, approximate that area using Riemann sum, and then we're also going to calculate its exact area using SymPy. But you don't have to worry about those calculations. For this exercise here, you just want to show the area. Okay, and then the other important thing to include in this plot is these thick X tick marks here, all of these black tick marks here. Those show the bounds for the rectangles that we are going to be using to estimate area. So this is one bound, this is one segment, this is another subinterval. I'm using all these different terms here that people use. But basically the idea is we are going to discretize this function into 14 bins, and these are the boundaries of the bins, and then calculate rectangular areas of each bin, and then use that to approximate the total area under the curve. Now, again, those approximations come in the next exercise. I'm just explaining what these tick marks mean. Now, these tick marks are exactly what you created in the previous exercise. These are the breakpoints from the previous exercise. So here I have the Python function, very simple. You can write it out all on one line. You could also do this with the lambda expression if you prefer. That's all fine. So the function takes x as input and it returns the evaluation of that function for those x-axis points. Okay, and now here I have the x-axis grid for plotting. You can see I start the plot a little bit before point A and a little bit after, and end the plot a little bit after point A. And this is 800, I don't know why I came up with that number, 809. But what I want to express here is that there's a distinction between the x-axis points that we are going to use for approximating the area of the function. That's what we did up here in the previous exercise, and there I only used 14 points. That's for approximating the area. And here I'm using 800 points. This is for the visualization. Okay, so we often have different x-axis resolutions for calculations versus visualization. Okay, and that's a key idea here. Okay, so here I'm plotting the function. That's pretty straightforward. This acts V line. This plots vertical lines, another vertical line. So this is for the lower integration bound, the upper integration bound. This is H line that plots a horizontal line at x equals 0. And yeah, it's going to be a lighter line and dashed, and that's called y equals 0. Okay, and then here is where I calculate the x-axis points for the area. So the area is calculated for, the area is visualized, not calculated. We'll get to that in the next exercise. The area, that patch that I'm using the function fill between for, is x values between a and b. Okay, so it's x values between a that are greater than a and less than b. Again, you can see the distinction here between the x-axis resolution for visualization versus the x-axis resolution for calculations and approximations. Okay, so yeah, fill between, I specify the x-axis values and the y-axis values. In this case, the default is to fill between these values and y equals 0. You will see in a later chapter, I think it might be chapter 17, when you draw areas that are not don't have a lower bound of the x-axis, then you need to specify additional inputs here. But for now, this is good. Okay, and then here's the breakpoint. So I loop over all the breakpoints, and I'm just, drawing a black line at each breakpoint. And that's it. That's how we create this figure. Now we have our breakpoints, we have our function, we have our visualization. We are now ready to approximate the area under this curve using various rules of Riemann summation. That's coming up in the next exercise. Here in exercise 3, we are now going to approximate that shaded area that we drew in the previous exercise. We're going to do this 4 times. It's actually only 3 approximations. We're going to do Riemann approximations using the left rule, the right rule, and the midpoint rule. And then a 4th time, we're going to use SymPy to determine the area analytically. So we get the exact value from a symbolic calculation. So then we will be able to evaluate the accuracy of these different approximations from these 3 different rules by comparing them to the result of the SymPy integration. So here we see the SymPy result, and here is for the left, the right, and the midpoint rule. You can see, well, I'll have more to say about this when I show the code. Once you have the variables already set up, as we did in the previous exercises, in particular exercise 1, the actual implementation of the Riemann sum is fairly straightforward. You can see it's literally just one line of code to get the approximation in each of these rules. Now, of course, it's more lines of code because I have a line of code to define the Python function that implements or evaluates the mathematical function. This is the vector of breakpoints that we defined in exercise 1, and this is delta x that we also defined in exercise 1. But once you have all this stuff set up, it's pretty straightforward. So remember, the Riemann sum is the sum of all of the areas of rectangles. Now, the area of a rectangle is the length times the height. Or the width, I should say. So the width is delta x, that's the width on the x-axis, and the height is simply the function value, and that's what we get from this Python function fx at the breakpoints that we've specified. Okay, so here for the left rule, we use the first, so we have n segments, n intervals, and that means we have n plus 1 breakpoints. So we use the first n breakpoints. This gives us the left corner, the upper left corner for the function values. And for the right rule, we use the upper right corners of the rectangles. And so the breakpoints correspond to, from the vector, we skip the first one, and we go from the second breakpoint until the end of the breakpoint. So this is something that I discussed in the book. Okay, and then the midpoint rule is the average of each successive pair of breakpoints. So that you see here, I'm taking from the breakpoints from the first one to the penultimate plus the second one to the final, and then I add those together, and then I divide by 2. So this gives me the average of each successive pair of breakpoints, which is the point in the middle. Okay, so it's that simple. And then here is where I'm calculating the integral, the definite integral, using SymPy. So I haven't yet defined this function as a symbolic expression. And now in this, for this example, we don't actually need this expression anywhere outside of this one line of code. So therefore, I decided not to create a separate variable and simply write the expression directly in sim.integrate. If you wrote this as a separate variable, that's great. That's totally fine. Okay, so we integrate this. Here I'm using a symbolic variable t. That's just to avoid overwriting variable x. And then here I specify as a tuple for the second input of sim.integrate the variable that we are integrating over, and then the lower bound and the upper bound for integration. All right, and then, yeah, the main thing I want to say here is that all of these approximations are reasonably good. Some of them are closer to the SymPy analytic calculations. Some of them are a little bit further away. It looks like using the left rule is the least accurate. It looks like it's further. Yeah, it's a little bit of an underestimate. But the wrong conclusion to draw here is that the left rule in general, always for every function, is going to be a worse estimate of the definite integral than these other rules. That happened to work out in this particular case, but that's because of this particular function and this particular bounds for integration. And that you're going to see, again, we're going to return to this question in exercise 5. But for now, we're going to go to exercise 4, and that's just about visualizing these partitions that we calculated up here. Exercise 4 has a fairly simple goal, but it does get a little bit thick into the matplotlib coding. So this exercise is going to be a great opportunity for you to test and improve your visualization matplotlib skills. So basically all you want to do is recreate figure 13.3, and I'll scroll up to that. But basically, my recommendation is to start simple, start small, start writing code to do one little piece of the figure at a time, and then slowly make your code a little bit more sophisticated each time you have finished drawing one little object in the figure. And in particular, I definitely recommend using for loops to draw each of the rectangles separately. Here is the figure that you are going to write code to produce. Now, the titles of each of these subplots contain values that you have already calculated. These are the approximations from the previous exercise that we calculated with the Riemann rules. Okay, so, and then, code for drawing the function line and these vertical lines indicate the lower and upper bounds of the integration that you also already have code for from exercise 2. So the main difference here, the main new point in this exercise is looping through and drawing each of these rectangles. So here's the rectangle for the left rule. You can see that the upper left corner of each of these rectangles touches the function line. Here's for the right rule, and here you see that the upper right corner of each rectangle touches the function line. And of course, the midpoint rule, we have the center of the bar touching the function line. Here is my solution. This is my code for drawing that figure. So first, I have this for loop over here that goes through all of the axes. So I'm looping through the 3 axes. And here I'm drawing whatever is common in each axis, right? So every axis every subplot has exactly the same function and exactly the same 2 bounds of integration. So far, so good. That's pretty straightforward. And now I have another for loop, and this for loop is organized differently, right? So here I'm looping over the 3 subplots, and here I'm looping over the 14 rectangles. So then within this subplot, or within this for loop, I'm drawing the rectangles. So a piece of code for each individual rectangle, for each element in this for loop. And now it's in the left subplot for the left rule, for the middle subplot for the right rule, and for the right subplot for the midpoint rule. So for these bars, for the left rule, you can see I'm filling between. So I'm drawing 4 points here. I'm specifying 4 points that will be filled in with black and an alpha or a transparency value of 2. And the 2 x coordinates correspond to the breakpoint and then the breakpoint plus delta x that comes straight from the formulas. And then the function is the function value at the breakpoint. Now, because we are looping from the first breakpoint, then this corresponds to the left rule. Now for the right rule, you can see that this line is almost exactly the same as this line. except here, so the x values are the same as they are here, and the y values are different. So here, the y values are just the breakpoint, and here it's the breakpoint plus delta x. So now this is going to draw to the right upper corner of the rectangle. And then finally, we have the bar for the midpoint rule. This one is a little bit more complicated. There's multiple ways that you can solve this one. The way that I chose to do it was to redefine this variable breakpoint, or BP. So here I define BP to be the breakpoints that we defined in exercise 1. Here I'm saying the breakpoint equals itself plus 1/2 of delta x. So essentially what I'm doing is shifting this breakpoint so that instead of corresponding to the left breakpoint, it corresponds to the center, which is the average of two neighboring breakpoints. Now, because that's the average, we need to change the x-axis coordinates. So it's the middle of the breakpoint minus 1/2 of delta x until the middle of the breakpoint, or the two breakpoints plus 1/2 of delta x. And now this is just f of x here. This looks like it's the same code as here, except, well, the code is technically the same, but I've redefined the variable BP. So these values here correspond to the left edge, and these values correspond to the center of the rectangle. Okay, I hope that all makes sense. Once you see the code, then I hope you appreciate that it's not so difficult thinking about how to calculate and visualize the left rule, the right rule, and the midpoint rule. And then, yeah, these are the, let me scroll back up here. These are the variables that we calculated, the approximations that we calculated in a previous exercise. And that's what gives us the nice figure that we have here. Here in exercise 5, we will systematically vary the number of partitions for the approximation from 5 partitions to 190 partitions using the same mathematical function and the same bounds of integration that we used in the previous few exercises. So essentially what you want to do is copy the code that estimates the area under the curve for these 3 different rules, the left rule, the right rule, and the midpoint rule, and just paste that into a new for loop where you loop over the number of iterations between, the number of partitions between 5 and 190, and then store the approximations for these different rules from each number of partitions, and then make a plot that looks like this. And here we have a horizontal line corresponding to the analytic solution. This we have already calculated in SymPy. I have a few remarks to make about this particular set of results, which I will discuss after I show you the code. So this code is actually not very difficult once you have already implemented the formula for calculating the breakpoints and also the actual calculations of the approximations for the different Riemann sum rules. Here I specify the vector of n's, and let's see, this is for storing the results. So you see it's going to be a 185 by 3 matrix. Okay, and then inside this for loop, I have to recalculate delta, right? Because delta x is going to change as the resolution changes, of course. Redefine the breakpoints. You can see here I'm using numpy.linspace instead of the list comprehension method that we explored in exercise 1. That's basically just because, this takes up less code. So I kind of prefer this method. And let's see, yeah, here we have the left rule for summation, the right rule, and the midpoint rule, exactly as I coded it a few exercises ago. It's really that simple. And then I plot each of those here, and then here I'm plotting the analytic result from SymPy. Okay, let's see how these results look. So a couple of remarks, a couple of things to notice about this plot. One is that it looks like the right rule overestimates while the midpoint and left rule underestimate. Again, as I mentioned in the book, and I've also mentioned this in an earlier exercise from this chapter, that is true. I mean, that really is happening. But the wrong conclusion to draw is that it's always the case that it will follow this pattern. There are other kinds of functions and other interval bounds where you might see exactly the opposite. So, for example, where the right rule is going to underestimate and the left rule will overestimate. In fact, you'll probably get that outcome if you just flip the sign of the math function, right? So just multiply the math function by -1, and you might find the reverse of this. The midpoint rule does seem to converge really quickly. Again, that happens sometimes. It's not guaranteed to happen. But what is really consistent in this figure that you can draw conclusions from is that all of these approximation methods will converge to the analytic method as the number of partitions increases. It's not always going to be an overestimate or underestimate. It's not always going to happen after, 121 partitions. Sometimes it'll take more partitions, sometimes less. If the function is linear or only has a few nonlinearities, then you might only need like 3 partitions to get a really, really good approximation. But in general, you will always see that as the number of partitions increases, the estimations become increasingly accurate. And of course, the true analytic result comes from applying any of these rules and then having an infinite number of partitions, or at least, as the number of partitions grows to infinity, then any estimation rule is going to asymptotically approach the analytic rule. Here in exercise 6, you are going to implement the trapezoid rule. Now, I do not want you to use SPI.trapezoid. This is the trapezoid function that is available in the SciPy.integration module. Now, to be clear, and I say this down here in the footnote, the trapezoid function is great. I actually very strongly recommend using either this function or the Simpson function in SciPy for real applications. So definitely use this function in the future. But for this particular exercise, I don't want you to use that. Instead, I want you to use NumPy and just implement the trapezoid rule manually. And the goal here is to make sure that you really understand how the trapezoid method works. All right, so all that said, here's the function. So f of u is u to the power of 4 minus 0.5. So that's just a fourth order polynomial, and then it's shifted down a little bit on the y-axis. You should use 6 partitions between these bounds, minus 0.5 and 1. And then you can color each bar according to the sign of its area. So you're going to create a figure that looks like this. So here we have the function in the black line. So that's u to the power of 4 minus 1/2. And then here you can see 1, 2, 3, 4, 5, 6 trapezoids drawn on top of this to estimate the area of this function. And then you can see I've drawn the trapezoid faces to be red-ish, like a light red, if they have a negative net area, and green if they have a positive net area. Now, this is an interesting case over here because we get both a negative area and a positive area inside the same trapezoid, but the whole thing got colored green because overall there's more positive than negative values. So this would be considered an estimation error. The function is actually below the x-axis here. So the function takes on negative values, and yet this entire window here is contributing, including this little piece, is contributing positively to the estimate of the net area. So that's wrong. But it's okay. It's an estimation error. And of course, as you increase the number of bars, so decrease delta U, then these trapezoids are going to be smaller and smaller. They're going to get thinner and thinner, and the estimation errors eventually go to 0. So we don't have to worry about this for the analytic calculations of area. This is just something we get from this very coarse resolution approximation. Okay, anyway, so you want to calculate the net area and the total area if you use my parameters, so delta U equals 0.25 then you should get these numerical values as approximations. Here I define a function for the function. So it's a Python function, fu, that stands for the function of variable u. There's nothing else that this could possibly indicate. So f of u, and yeah, that returns u to the power of 4 minus 0.5. Okay, here are the partition parameters. Here I specify the breakpoints. Remember this from exercise 1. Of course you do. This is defining the breakpoints based on the boundaries and the number of partitions. And then here I am specifying the vector of u points instead of x-axis points. These are u-axis points for visualization. And as I mentioned a few exercises ago, there's a distinction between the resolution that we use for visualization versus the resolution that we use for calculations. So in this case, as in many other situations, the visualization resolution is higher than the resolution that we actually use to calculate. So in here I plot all those. It's a lot of U's hanging out over here. Okay, let's see. Here I'm plotting the rectangles and also calculating the area, the net and the total area in the same for loop. So with the standard, like the standard Riemann summation rules, like the left rule, the right rule, and the mid rule, you only need to know the function value at one point, right? That's either the left point or the midpoint or the right point. With the trapezoid rule, we actually need two function values corresponding to the two upper corners of the function. So that's why I have L, so the value of the function at the left corner and the value of the function at the right corner. And that is this breakpoint and then this breakpoint plus delta U. Okay, and then here is where I'm drawing the rectangle. You can see this looks just like it did for the previous exercises, drawing a bar. And now this is different, right? Because previously we had the same y-axis value for the two bars, but now we're not using rectangles, we're using trapezoids. So we have the same lower right two edges and different upper edges. Okay, yeah, and then this is code to specify the face color. And here I just say, you know, if the face color is negative, then use red, and if it's positive, then use green. Okay, and then here is the trapezoid rule. This is how we create or calculate the area of a trapezoid. It's the width times the height, and the height is the average of the two upper corners. Okay, so it's either that raw average, which would be for the net area, and the total area is exactly the same calculation, but we take the absolute value instead of just the raw value. Okay, I hope that's all clear. This is essentially just translating from the math that I described in the book into Python code, and here we see the figure. Exercise 7, and also the next several exercises, will focus on using SymPy to calculate exact definite integrals both for net area and also total area. So let's begin with this exercise. Here you want to implement these three functions in SymPy, so as symbolic expressions. I called these f, g, and h, and these are functions of tau instead of x, just, I don't know, just to give some variety. I am a big fan of the letter x, but it's also nice to use other letters and symbols sometimes. Okay, anyway, what you want to do is calculate the total and net areas of each of these functions, all within the same integration interval, or using the integration bounds of minus 0.5 to plus 1. And then you want to generate or write matplotlib code to produce figure 9. Okay, so let me scroll up to figure 9 to show you what that looks like, and then I'll switch to the code. Here you see figure 9, and the idea is that we have these three functions, f, g, and h, and we are calculating the area. So we're visualizing the area that we are calculating. Now, the point of this figure was to illustrate the distinction between net area and total area. So in this case, the function takes on both positive values and negative values. And that means that, you know, some of these positive and negative bits will cancel each other out. And that's why the net area is closer to 0 because there's some cancellation. And the total area is like all the gray pixels. So this contributes negatively to net area, but positively to the total area. Okay, here we have a case where the function itself takes on both negative values and positive values, but inside the bounds of integration, there are only negative function values, and therefore the net area and total areas are the same magnitude but different sign. And of course, this is negative because we have negative function values. And then over here, we have the opposite. So we have the net and total area are the same because the function only takes on positive values within the integration window. In fact, for this particular function, this particular function can only ever have positive values. It never equals 0 and is never negative. But that actually doesn't matter. The range of the function for the entire domain doesn't matter. What we care about here for net versus total area is only what happens in the function within the integration bounds, within these intervals here. Here I am creating a symbolic variable, tau. Now, I've mentioned this before, but just as a quick reminder, when you use these Greek terms so the words for Greek letters, when calling sim.symbols, then SymPy will know that TAU is not 3 different letters or Latin letters, but instead is one Greek letter, tau. Now I'm also calling it tau as a variable. That is just for convenience. I could call this variable ASDF, and it would still print out in SymPy and LaTeX as the Greek character tau. Of course, this is confusing, so it's better to use this. Okay, here, so there are multiple ways that you could set up this code to run for these 3 different functions. What I chose to do here is create a list. So this is a Python list, and it has 3 elements. Each element corresponds to one of the functions that I showed in the book text. Now, there's several ways you could have alternatively set up the code. For this, that would be correct, which is fine. When I write teaching code, I like to give some different options so you can see different styles. You're exposed to different ways of setting up the code. So that gives you a little bit more flexibility to adapt your code to whatever is best for your specific project or application or whatever. Okay, anyway, here I'm creating the x-axis grid. I guess I could have called this the tau axis grid. And here is where I specified the bounds, and this is the x-axis values or tau axis values that I'm going to use to draw in the patches for each of the intervals for the 3 different functions. Now, because we are evaluating the integrals, the definite integrals, using the same integration bounds for all 3 functions, we can actually define these variables outside the for loop. Okay, so then here is where all the action happens. This is a for loop. I'm looping over the different functions. So the 3 functions in this list, the 3 axes that I create here with subplots, and also these 3 letters. This is just for naming. So the functions are going to be called f, g, and h. This is the function letter. Here I evaluate the function numerically to get a numerical array using the substitution method and list comprehension. Here's where I plot the function. It's all pretty straightforward. I think you've seen all this code before. And here I'm using the function fill between to draw the patches from, or 1 patch per axis for these x-axis coordinates and these function values. And here is the key calculus part of this code, this for loop. I'm using SymPy to integrate either just the function within these bounds for this variable or the absolute value of the function. And this is how we get the total area. So it gives us the net area, and this gives us the total area. Now, this is theoretically sound. You integrate the absolute value of the function. That's also fine for approximation. If you use it for symbolic expressions to get the exact analytic result from symbolic calculations, this works sometimes. It should work in theory. It should work every time. But you will see cases, in fact, you'll see a situation in the next exercise where this actually fails. This gives the wrong result. And I will explain later how to deal with situations like this. Anyway, it's going to work for this particular case because these functions are all fairly well behaved and they're easy to calculate for the absolute value. Okay, yeah, and then just setting some access properties and so on. So that is for this exercise. I hope you found it useful, and I'm waiting for the plot to generate. Okay, now we see the plot. All looks very nice. Welcome to exercise 8 of chapter 13. This is an action-packed video, or at least an action-packed exercise. There's a lot going on here. I'm going to go back and forth between the book text and the code a few times to walk through this exercise piecewise. Okay, so the first step is to implement this integrand as a symbolic expression in SymPy, cosine of x. Super duper simple, guys. That part is not going to give anyone any difficulties. Now, what we want to do in general in this exercise is visualize this integral, this definite integral, and then use SymPy to calculate the analytic or exact definite integral between pi over 2 and 5 pi over 2. So we want the net area and the total area. Now, I have discussed in the previous exercise and also earlier in the book, in this chapter, that you can calculate the total area using an expression like this. So basically, all we have to do is take the absolute value of the integrand to get the total area. I've also said that this can be tricky. This is theoretically sound, but in practice, it can be really difficult to implement because of the difficulties of integrating composite functions. So therefore, what you're going to additionally calculate here is this integrand. I call this area total, and then the S is for split. So basically, we want to split this integration into two smaller integrals, each of which has the same sign. So now the absolute value happens after we perform the integration. So the integration is just on the cosine of x. That is very easy to integrate. And then we take the absolute value of the resulting definite integral, which is just a number. So that's really simple to calculate the absolute value of. Okay, so the question is, what is this splitting value here? I just call it S in this case. Now, the upper bound has to match the lower bound here so that we are still traversing the entire integration interval. Now, in principle, you can just look at a graph and figure out what this value of S needs to be. But what I want you to do is learn more about SymPy and basically figure out how to get this expression in SymPy. So I want you to use sim.solveSet. This is a function we've used sometimes. More often we use sim.solve because it just is the output is just a little bit easier to work with. But there are certain kinds of expressions that sim.solve struggles with and sim.solve can evaluate, including specifying the domain. So what you want to do is specify that the domain to solve for S, this splitting variable, should be in the open interval of pi over 2 and 5 pi over 2. Now, why do I say the open interval? The reason is that here we have pi over 2, and here we have 5 pi over 2. Now, we do not care about this point here where the function crosses 0, and we do not care about this point here at pi over 2, where again the function crosses 0. So if we were to solve for the cosine of x equals 0 for the closed interval of pi over 2 and 5 pi over 2, we would actually get 3 results. Okay, we would get this result here, and this one, and this one. But we already know that these two are the bounds, right? So all we care about is this point here. We want to know the value of this point here. So therefore, we want the open interval of pi over 2 and 5 pi over 2. Okay, so don't worry about the graph yet. That's going to come up. That's like part 2 of this exercise. First, just figure out how to solve for S in this integral over here. Here we are in the code. I'm defining a symbolic variable. Here's the function, super simple, and here are the two bounds. Now notice that these two bounds are symbolic variables. Sometimes when we are calculating definite integrals, we can use numeric variables like numpy, but in this case, we want to use symbolic variables, sim.py. Okay, and here's where I call solve set. I want to solve for the function implicitly set to 0, variable x, and here I specify the domain equals sim.interval.open between a and b. And this is the reason why I want these limits here to be, or these bounds to be symbolic and not numeric, so that SymPy will correctly interpret this open interval. Okay, so let me show you first, before worrying about this thing, let me show you what happens. Maybe I'll just do like this. Okay, so now we see that the answer is basically that, the solution is 2 pi times n for n in the natural number. So this is telling us that any numerical value, any number, 2 pi plus pi over 2, or 2 pi times some integer, plus pi over 2 is going to give us a value of 0. So that's great, but that's not exactly very helpful because we're only looking for one specific value between these 2 points. Okay, so that gives us this result here, which is just one number. So this is 3 pi over 2. This is the correct answer. This is the value of s that splits our function in the interval into 2 parts, where we have a negative lobe and a positive lobe. Okay, and now it turns out, this is a SymPy set object. We can look at the type of this. This is not so easy to work with. It's a finite set. So what I want to do is extract this at the actual number, the symbolic number 3 pi over 2, from the output, which is a set. So to do that, we get the arguments, so .args. This is a property here, and this gives us a tuple. Now this is just a one-element tuple, and I want that one element. So therefore, I'm getting args 0, and this is the splitting variable. Now for the second part of this exercise. The second part of this exercise is doesn't involve calculus. This is just visualization. So you want to basically generate this plot, or a plot that looks something like this. What I have tried to depict here is that this lobe will contribute negatively and this lobe will contribute positively. So I've drawn these hatches as minus signs. It looks like, big horizontal lines, but these are a bunch of minus signs, and these are all plus signs. I've also colored them. These are red and these are green. Previously, I've just colored these with grayscale patches. You can also make solid color patches. I want to give you some variety, some different options for visualization. Okay, so now I will switch back to Python. I'll show you the code to generate this figure, and then we will come back to the book text and work on part 3 of this exercise. Here I am lambdifying the function so that I can extract any y values that I want for any x-axis values that I create. Here are the x-axis values. I'm going from the lower bound -1 to the upper bound +1. Now remember that I specified a and b here to be symbolic variables, and so in order to use them as numbers, we need to convert them from SymPy objects, from symbolic expressions, into floating point numbers. So there are several ways you can do that. You can explicitly convert them to NumPy. You can also just convert them to floating point numbers like this. Lots of ways you can do this. Okay, here I plot the line corresponding to the function. No problem there. Here I'm just drawing some a horizontal line at y equals 0 and some vertical lines corresponding to the lower and upper integration bounds, and here is for the splitting variable. And here's where I plot. So this is fill between. You've seen this many times before. What might be new here is this hatch option. So here's where I specify the symbol used to color in the hatches or fill in the area with hatch marks. So minus sign and they're red, and plus sign and they're green. Okay. And that's basically it. Then, just some setting some axis labels and so on. And that's how we get this plot. Here we are back in the book. And now I'm going to show you basically the third part. The last step of this exercise is to actually calculate these areas, the net area and the two methods of calculating total area. So this part you can use code that you've used before. Basically, it's sim.integrate to calculate net area and total area. And then here, unfortunately, this ended up splitting up across two different pages. But basically, this is the other way of calculating total area, not as the absolute value of the function, but splitting up the integral and then taking the absolute value of the mini integrations within each segment of the function where the sign is constant. Okay, and here we can see the results. Now this area here is 0. The net area is 0. That should be intuitive. We have this lobe here and this lobe here, and they perfectly cancel each other, right? So the area here, whatever that area is, it happens to be 2, but it doesn't matter. This area and this area are the same magnitude but opposite signs. So the net area from here to here is 0. Okay, and then here we have that the net area of each of these mini segments, these little intervals, is 2. Now this one is minus 2, this one is plus 2, but then we take the absolute value, and 2 plus 2 is, what is 2 plus 2? Pretty sure it's 4. Okay, so there we get that. Now, this number here also needs to be 4, okay? This is the total area calculated through the absolute value of cosine in these same bounds, and here SymPy gave us an answer of 2. This is an error. This is not supposed to be that way. This is a situation where SymPy is struggling with this composite function. So taking a trig function that repeats infinitely and puts it inside of a absolute value function, and the integral of that, the indefinite integral of the cosine embedded inside the absolute value function, is a piecewise function with an infinite number of pieces. I'm going to have more to say about this in the next exercise. So here you see the code. To get net area, we just integrate the function for variable x in these bounds. This is the total area by absolute value. This is exactly the same code that you saw in the previous exercise, which worked fine. And then, so then I have splitting by area. So here I have all of this is, let me see, this you recognize. Here I'm integrating function f, variable a from a variable x, from the lower bound to the split variable. And then whatever is the output of this is some numerical output or symbolic output, but then take the absolute value of that. Notice the difference here, the absolute value of the function versus just the function, the cosine of x, and then the absolute value of the definite integral. And then this line is the same, except instead of going from a to s, we go from s to b. Pretty straightforward. Then I'm adding these two areas together. Okay, and then, this LaTeX coding gets a little bit hairy, goes on quite long, but essentially it's just printing out the results that you see here. Again, this is correct. The net calculation is correct. This total calculation is correct by splitting. SymPy struggles to accurately integrate this composite function, and therefore gives us an incorrect result. Here in exercise 9, we will continue using SymPy to explore and understand definite integrals, in particular net versus total area. There's actually 3 parts to this exercise, 2 main parts, and then there's a third bonus part that I'll get to at the end. Okay, so the first part is an investigation. What you want to do is implement this function, f of x equals x squared minus 2x, in SymPy, so a symbolic expression. Then you want to calculate the net and total areas of this function, this polynomial, using sim.integrate. And the idea of this exercise is to systematically vary in a for loop the upper bound of integration. So the lower bound is always going to be minus 1/2, and then the upper bound is going to vary in different at different iterations of the for loop. So I hope that makes sense. So basically, you're going to calculate the definite integral 30 times, each time in a for loop. Each time, the lower bound of integration is the same, it's minus 1/2, and the upper bound of integration will change. It's going to start off at the beginning of the for loop at 0, and then by the end of the for loop, it's going to be an upper bound of 3.5. And then here you can generate this figure. So here we see the function, nothing particularly crazy going on here. It's just, x squared minus some offset. Okay, and then what you're looking at here in panel B are the two areas. So we have the net area and the total area from all of these different iterations of the for loop. So the black squares correspond to the net area. Now remember, the data are only being shown here at x equals 0, or I should say b equals 0. And that's because the definite integral always starts off with a lower bound of 0 and an upper bound, lower bound of minus 0.5. And these are the varying upper bounds. You can see that the net area starts off being a little bit positive, right? Here is a little bit positive. And then we start to get more negative area than positive area. And so then the net area gets negative, and then eventually, somewhere around 2.9 or something like that. I don't know the exact value, but somewhere around here, all of this positive area and this positive area here eventually cancels out this negative area here. So the net area becomes positive again. Now the total area, in contrast, can never be negative. We can never have a negative total area because we're always working with the absolute value of the function or the absolute value of the definite integral. So the total area is, in this kind of investigation, is what's known as a monotonic function. Monotonic means it can only ever go up or stay the same. It can never go back down. That's a monotonically increasing function. You can also have a monotonically decreasing function where it can go down or stay the same but never go up, but that's not the case here. Okay, so this is the first part of this exercise. I will now switch to Python and show you the code before coming back to the book to get to the second part. I really enjoy these kinds of exercises where we do systematic investigations and evaluations, but there's nothing particularly new in this exercise. Okay, so here we are creating a symbolic expression for the function x squared minus 2x. Here I'm listing the values of b, the upper bound, and here I have a for loop where I integrate the function itself, or I integrate the absolute value of the function. Okay, now, as you know from earlier exercises, you could also implement this by finding the splitting value, finding the exact numerical value where the function changes from having positive values to negative values and back to positive values, and then, running separate integrations for those pieces. But this is how I solved it here. And here you see I'm using, as the second input to sim.integrate, a tuple with the variable that we integrate over. The lower bound is fixed to minus 1/2, and the upper bound varies. All right, so that's that. Pretty straightforward. And don't worry about this commented line. That is the bonus part of this exercise. And here I'm doing the plotting. Okay, so here I am using substitution and list comprehension to evaluate numerical values for the function, which I plot here along with some lines. And then here's where I plot the net area and the total area. So great. So far, this part of the exercise is really just about you gaining more experience with working with SymPy. Here is the second part of the exercise. Use SymPy and LaTeX printing to show the antiderivatives for the net and total areas of the function. So here we see the antiderivative of this function, x squared minus 2x. This is not me handwriting this out in LaTeX code. Instead, this is SymPy calculating the antiderivative using sim.integrate and then printing out using LaTeX. And then I just copied the LaTeX code. Okay, now here is for, here you actually see the antiderivative, right? So there should be a plus c here, but you know from earlier chapters that SymPy just does not by default print out a constant integration. Here we have a more interesting situation. So here, we asked for the integral of this function, and the result of sim.integrate was just exactly what we inputted, right? So these two sides of the equation are the same. And the issue here is that SymPy is not able to evaluate this expression analytically. So therefore, what I want you to do is include some bounds of integration. And then, yeah, I'll have some more things to say about this when I show the code. So here is calculating the antiderivative, right? So this is sim.integrate, exactly the same function, exactly the same code that we use here. The the only difference is that the second input includes bounds here, and then that gives us a definite integral. And if you do not include bounds, then you're going to get the indefinite integral, or the antiderivative. So for the function and for the total area, the absolute value of the function, and then we can print this out like this. Okay, so then, yeah, you see here we get a result that we expect. Here we get a result that isn't a result. It's just we're asking SymPy a question, and here we get the answer. Here we don't get an answer. SymPy is just telling us the question back again. Again, this is because SymPy is just not able to calculate an exact analytic solution for this antiderivative, and or this integral. That's really just because the absolute value function is just tricky to integrate when we have functions that are also varying between negative values and positive values. Okay, and then the final thing that I wanted to show you here. Here we see one of the reasons why integration with the absolute value of a function can be tricky to evaluate. The integral itself is a piecewise function because it depends on the sign of the function for each particular value of this integral here. Now, SymPy actually can calculate a numerical result. It's not showing a numerical result, but if we would ask for eval f, then SymPy would actually give us an estimate of that exact result over here. Here is the final part of this exercise, which I call the bonus part. Basically just repeat the exercise, but using the cosine of 2 pi x instead of that polynomial function. Okay, so something interesting is going to happen, and I will show you that in a moment. And yeah, I'll also have some interpretations about this. Let's look at the code. So here we are back at the top of this exercise, and all I'm going to do is uncomment this line. So now instead of f being equal to this polynomial expression, it's this trig expression. You can already see some difficulties here. SymPy took 8 seconds to run through this code here, whereas it took only like a second or two for this one. So it's already encountering some issues here. All right, so now let's make this plot. And here we see that here is the function itself, very simple, just cosine. Now here we can already get suspicious. Okay, so the net area is fine. There's nothing wrong with how this looks. The total area should be ringing alarm bells for you. There's no possible way for the total area to decrease when we increase the interval of integration. Remember, total area can only be a monotonically increasing function. So there's no possible way to integrate over a larger window. I have more area of the function to integrate, total absolute value, and the total area calculated by this definite integral decreases. So this is just not possible. This is something that I introduced you to in the previous exercise. You saw that SymPy was having difficulties with absolute values of trig functions. And yeah, as I mentioned at the end of the previous exercise, the issue here is that the definite integral is a piecewise function with an infinite number of pieces, and it always depends on the sign of the cosine function. And actually, let me make this even more clear. So what we are integrating here is the absolute value of this function. So in fact, for calculating total area, the function, it looks like this. It's just bouncing up and down over time. Okay, and then basically where I want to lead with this is into the next chapter where I will introduce computational methods to estimate the definite integral using numerical methods available in NumPy, but in particular in SciPy. That's going to give us very accurate results, and it's going to completely resolve these kinds of difficult situations. In practice, in applications, you are rarely, if ever, going to solve integrals analytically. Instead, you will solve integrals, in particular definite integrals, using numerical approximation methods that give you much broader range of access to different kinds of complicated functions, and you learn all about that in the next chapter. Exercise 10 and also exercises 11 and 12 are focused on implementing the Lebesgue integral and comparing the Lebesgue and Riemann integrals or approximations for a particular function. Okay, so we have to build up to this over a couple of exercises, in particular because the Lebesgue approximation is a little bit tricky to implement in code and also to visualize. So we have this big goal of comparing Lebesgue and Riemann approximations, and that takes 3 exercises to work through. Fortunately, we're going to start off pretty simple and straightforward. The goal of this exercise so exercise 10 is to implement a Riemann sum and its associated graph. There's nothing new. Well, the visualization has some new aspects, but there's nothing new in terms of math or calculus in this exercise. Again, this is just setting us up for the comparison in exercise 12. Okay, so this is a great review of Riemann sums. What I would like you to do is basically create this figure here. The function is, where do I list the function? All right, the function is here in the legend. Okay, so we have x squared plus the cosine of 2 pi x divided by 5. So the whole cosine function is divided by 5, not the term inside the cosine. Okay, so now if you use 12 bars, you can create a figure that looks like this. And you get an approximate net area of 1/3. So 0.333 delta x ends up being 0.08333. And that comes from the fact that we are using n equals 12 bars. So 12 discretizations of this function between the bounds 0 and 1. You can copy, paste, and modify code from earlier in this chapter. But if you're up for a little bit more of a challenge, then you can try writing the code and the visualization for this exercise completely from scratch without looking back earlier in the chapter. That would be a really great review of the Riemann sum. Okay, the last thing I want to mention here is that I chose to use the midpoint rule. That's visually obvious that I'm using the midpoint rule here. Which rule you use doesn't matter for this exercise or the next 2 exercises. If you like the left rule, then go for the left rule. You want to do the right rule, then go for that. It's all fine. Here I have a Python function for this expression. So I call it function f of x, but then inside I call it variable u, but whatever. Okay, so there's the function. And yeah, I'm not going to spend a lot of time talking about this code here in this cell because this is code for the Riemann sum, which you've seen multiple times before, in particular in exercise 1 to do all of this stuff, and then in exercises 2 and 3 to actually do the calculations, the approximations, and the visualization. So here, because I'm using the midpoint rule, I'm shifting each breakpoint back by delta x over 2, calculate the area, and then sum the total approximate area as the function value times delta x. So this is the function value at the middle, the center between each successive pair of breakpoints. And then here's, fill between. You've seen this multiple times before, between the breakpoints and the function value. The only thing new that I've added to this code is setting the alpha parameter of this fill between function. So alpha is the transparency. You can see that the color of the bars is always black, but the transparency changes. It varies from 1 to 0 as I divided by 1 minus I divided by n. So n is the total number of bars that I'm drawing, and I is the looping index. Okay, so this exercise is pretty straightforward. I hope you found this to be a really good review of Riemann sum calculations and visualization. Now for exercise 11. This is an exciting exercise, but it's also quite challenging. It's one of the more challenging exercises to code possibly in this entire book, certainly in this chapter. What you are going to do here is implement the Lebesgue approximation of the function in the bounds that we explored in the previous exercise. So it's exactly the same function as in the previous exercise, same integration bounds and so on. But now instead of the Riemann sum, we are going to calculate the Lebesgue sum and the Lebesgue approximation. Okay, here is just a warning, fair warning that the coding is more difficult for this exercise than is typical for most of the exercises in this book. Okay, I break down this approximation method into three sections, three sub-goals. So let me first explain all these, and then I'll switch to code. Okay, so the first sub-goal is to partition the range of the function between the two x bounds. Now, why do we need to partition the range, or the y-axis? That is because the Lebesgue integral involves cutting up the range of the function instead of the domain of the function. Now, cutting up the domain of the function is easy because you don't actually need to know anything about the function to cut up the domain. Well, I guess you do a little bit, but you need to know, all you need to know is the bounds, and you need to know that the function is continuous within those bounds. And then, without knowing anything else about the function, you can already partition the domain. But it's different for the Lebesgue integral because we need to know the range of the function, and you cannot know the range of the function, so the total span of y-axis values, without knowing about the function and without evaluating the function. So let me show you what that looks like here. This is the end result of this exercise. It's going to be a figure that looks like this. So the bounds are the same as the previous exercise. The function is the same as the previous exercise. So to be able to discretize the range of this function, what you need to do is evaluate the function within the x-axis bounds, or within the integration interval. So you can do that with 1,000 points. So evaluate this function at 1,000 points between 0 and 1, and that's going to give you a high resolution for y. That will allow you to identify the range of the function. And based on that range, so it dips a little bit below 0, and then it goes up to whatever this is, 1.2 or something. So based on this range, then you can discretize into 12 partitions. So that's what I say here. So define a grid of 1,000 points, and then evaluate f of x, so get 1,000 values of the function, and then you can find the smallest and largest values of y. And from there, you can partition the range into n plus 1 linearly spaced numbers, and that is going to give you n partitions. Okay, and then based on those partitions, you can define delta y. I want to show you the code for that part, that sub-goal, and then I'll get back to explaining the second sub-goal. Okay, so we need to partition the range, but in order to do that, we first need to partition the domain, but here we're getting a high resolution. Okay, so this is a very high resolution. So we have delta x is going to be some very small number. Again, this is not used for the approximation of the integral. This is only used to evaluate the function, and that is going to allow us to identify the minimum and maximum values of the range. And that's what I get here. So the function values at this high resolution. Here is where I'm identifying the smallest number and the largest number in this evaluation based on this high resolution of 1,000 points here. And then from there, we get n plus 1 linearly spaced points between the smallest function value and the largest function value. And then this is going to allow us to create the sub-intervals or the partitions, the n partitions of the range. Okay, and then here I get my, oops, sorry, I clicked too many times. Here I get delta y over here, like that. That was the first sub-goal for calculating the Lebesgue approximation. The second sub-goal, so that was actually just setting us up, right? We're creating variables, defining the delta y and the partition points. The next sub-goal in this paragraph, this is actually what is implementing the Lebesgue approximation. So now what you want to do is measure the size of each y partition. So basically, now you have to loop over all of the y partitions and find all of the x-axis values that are within those partitions. So the y-axis for the function gets cut up into intervals, and you want to know what are the x-axis values that fit within each of those y-axis partitions. Okay, so you count that number of x-axis values for which the corresponding y values are within the partition. That gives you the sum, and then you scale by delta x, and that gives you the sum scaled by the x-axis resolution. Okay, so then you repeat this in a for loop for each of the y partitions, and that is how you get the Lebesgue approximation. Now, the final sub-goal, this is actually just visualizing. This is not calculus anymore. This is just matplotlib stuff. But this is also pretty tricky. This is trickier than visualizing the Riemann sum because you need to worry about the possible occurrence of repeated groups on the x-axis that correspond to the same y-axis value. So for example, if you find that all of the x-axis points in a certain range subinterval looks like this, 1, 2, 3, 7, 8, 9, 10. What you need to do in the code is for visualization. This is not for the Lebesgue approximation, numerical approximation. This is fine for the numerical approximation. But for the code, we want to separate this vector of points, this list of indices, into adjacent indices. So 1, 2, 3, that has to be one bar, and 7, 8, 9, 10, that's a separate bar. Okay, once you do all of that, that part gets really tricky. You're going to end up with a plot that looks like this. Okay, so here I have this for loop. Up here, I'm initializing the Lebesgue approximation to be 0, and then we're going to keep summing up into this number. Here I'm opening a figure and plotting the function. So far, so good. Okay, here is the for loop over n. This is the n range partitions. Okay, so now here what we need to do is find all of the x-axis values that are between each of the bound for each y-axis or range partition. Okay, so I hope this code is pretty straightforward so far. We have the y partitions, and yeah, we're looking for the function values that are within this particular partition. And then we just measure the size of this. So it's literally just the sum of these numbers. This is just, the output of this is Boolean, which converts to 1 and 0 here inside the sum function. So this is just looking at all the x-axis values and saying how many of these x-axis values are in the function between the two boundaries, and then multiply that by delta x. Okay, and then so this is called the measure or the size of that set. It's the set of x-axis values within each y-axis boundary. Okay, and then, yeah, then we just sum all of the values. So the size of that set multiplied by the average of the function value. And this is the Lebesgue equivalent of the midpoint rule, right? So you have the y-axis interval like this. And now when you are averaging the area, you need to know, is it, do you take the bottom or the top or the middle? So here I'm taking the middle on the y-axis interval, and this is equivalent to the midpoint rule for the Riemann sum. Okay, so this gives us the Lebesgue approximation. The calculus is actually finished here. Here we're done with the calculus. Sub-goal 3, this is just about drawing the rectangles. And I want to start by showing you all the way down here. Okay, so this is the final result where we have fill between for these x-axis boundaries and these y-axis points. Again, I'm setting the color to be black and the alpha to be to range as a function of the partition number. Okay, so now with that as the endpoint, I'm going to slowly walk back. So here, these three code options here are for different ways of visualizing the Lebesgue approximation. This option C, this is what I actually used in the figure. This is drawing the bars horizontally. If you want to explore these other visualization options, again, this is not changing the calculus. It's not changing the algorithm. It's just a different way of drawing the bars. You can comment out, for example, comment out option C, and then we will visualize option B, which I'll show you in a moment. Okay, and then this code here is finding all of the x-axis values that are contiguous. So we have this set of x-axis points that are within each partition, so within each subinterval on the y-axis. And basically all that this code does is find where we have discontiguous points and then break them up into separate segments. And that's what I do here. So group starts and group ends. These are only going to be individual lists. So this is just going to loop once. If the x-axis values are contiguous within each range partition. Okay, so now all that said, so there's quite a bit of fancy code going on in there, but I hope it all makes sense. Okay, so here you can see I'm just drawing the bars a little bit differently from how I showed in the book. Now, these bars here are still vertical, so it looks like a Riemann sum, but notice that the width of the bars are different for different bars, right? So this bar is a little bit thicker, this bar is a little bit thinner. Here's one bar that's really wide over here. And why do these bars have different widths? That's because I'm actually breaking up the range and into equal size bins. So the y-axis width is the same, or the height is the same. So therefore the width has to vary. And that is because we are using the range to approximate the integral and not the domain. From the previous two exercises, we now have code to implement the Riemann sum and code to implement the Lebesgue approximation for this function that we've been working with and visualizing. The goal of exercise 12 is to directly compare the Riemann and Lebesgue approximations. So there's two parts to this exercise. First is just writing the code to set up for the experiment, and the second part is to do the investigation, where we increase the number of partitions, so we increase the resolution either of the domain for the Riemann sum or the range for the Lebesgue approximation. And we see how these two compare as we increase the number of partitions. Okay, and then we can also get an exact result in SymPy to compare. Okay, so that is the end goal. Let me first start by describing the first part of this exercise. The first part of this exercise is fairly straightforward. What I want you to do is create Python functions that implement the Riemann and Lebesgue approximations. So I implemented this as two separate Python functions, one function for the Riemann sum and one function for the Lebesgue integral. Now, one thing to keep in mind is that you can custom tailor these functions to be for this specific problem. So for this specific exercise, this specific function, you do not need to worry about making your Python functions be super generic to be able to work for any possible kind of function with any number of variables and any terms in the function. Don't worry about all of that. You want to write these Python functions specifically to solve this equation, okay, and to approximate the area of this expression. Okay, so one function for the Riemann sum, one function for Lebesgue approximation, and you want to make sure that you can vary the n, the number of partitions in both functions, because that is key to the next part of the exercise. Okay, and then also use sim.integrate to find the exact value, the exact definite integral, and that's going to be our comparison. Okay, so if you implement this correctly, then you can print out the results for the Riemann sum, the Lebesgue approximation, and the SymPy exact calculations. You should be able to reproduce my results. I'm first going to show you this code, and then we'll get back to looking at the plot. So here I have a function for Riemann, and yeah, this is literally nothing new. All I'm doing is copying and pasting code from the previous, or not the previous exercise, but exercise 10. Obviously eliminating all of the code for visualization. There's no visualization involved in this approximation. We've already seen that. And here's for the Lebesgue integral. You can see this function is a bit longer. There's more stuff that's involved. There's more steps in this algorithm. But again, all of the code here is not new. This is not new code. It's all copied from the previous exercise, and I have eliminated any code that was necessary for the visualization. We're not visualizing the Lebesgue approximation. Here, we are only calculating it. All right, and then, so let me run that code here to generate those functions. And here I'm doing the one experiment, so I'm not varying n yet. That comes up in a moment. Here I'm just running this calculation for n, and here I'm calling the two functions. Now again, you'll see that this is relying on variables that I created in the previous exercise, including the integration bounds a and b. These were also variables defined in the previous exercise. These are not functions that are designed to work for, not Python functions that are designed to work for any possible math function. It's really custom tailored for this exercise. Okay, and then here, this is for the exact integral in SymPy. And then I just call these functions and print out the results. So here we see both Riemann and Lebesgue are quite accurate relative to SymPy. They have the same, they both start off as 0.33. And then it looks like the Riemann sum is a little bit closer to the exact result. But yeah, I mean, this is a pretty small difference that we're talking about here. Once you have that code and those Python functions, then the rest of this exercise is pretty straightforward. So you basically just want to set up a for loop to vary the number of partitions for the domain or for the range. Start with 4 and go up to 40 partitions, and then basically just repeat the approximations, repeat the calculations over and over again. Obviously, you don't need to repeat the SymPy calculation. That's going to be the same every time. And then make a plot that looks like this. I will have some interpretations about what we see here after I show you the code. So here is the variable for the range of partitions, the different partitions that we're using. And let's see, here's the experiment is actually very simple in terms of code once you've already written these Python functions. So all I'm doing is changing this variable n. Now notice I don't even call this as an input variable. So I'm just leaving this as an external variable because these functions are really custom tailored for exactly this exercise. They're not designed to work for any random function. Okay, and then I'm just storing the results, the output of these, which is the approximation of the area by Riemann or the Lebesgue method. So pretty straightforward. Once you've done, I think, the previous exercise 11, that was pretty tough. Once you've done that, this is a little bit easier. Okay, and then, yeah, just plotting the results here. So what do we see? There's a couple of observations that we can make here. One is that both of these methods converge to the true result. Okay, so that's good. As we increase the number of partitions, we are getting a better and better approximation. And as you know, the approximations will become the true integrals, the true analytic exact result, as the number of partitions goes up to infinity. But you can see we don't even need to go up to infinity for this particular function. They'd be really, really close after maybe another, 10, 20, 30 partitions. Also interesting to see that the Riemann sum converges faster and smoother compared to the Lebesgue approximation with increasing partitions. Now, that is not trivially guaranteed to happen, but it does often happen that the Riemann sum converges faster and it converges more smoothly compared to the Lebesgue approximation. Now, you might be wondering why we even bother with this Lebesgue approximation. It's less accurate. It involves more code. It's weirder. It's harder to understand. So the answer to that question is basically you should always prefer the Riemann sum when possible. The Riemann sum is great. It works extremely well. It's accurate. It's sensible. The Lebesgue approximation and the Lebesgue integral is designed specifically for a relatively small number of failure scenarios in the Riemann approach. So if you study more advanced mathematics or like advanced physics, you will encounter failure scenarios where the Riemann sum doesn't work, where it breaks down. And in those cases, it's better to use the Lebesgue approximation. But most of the time, you're going to use the Riemann theoretical approach to calculating definite integrals and approximating definite integrals. And that's basically what we are going to be using for the rest of this book. I introduced the Lebesgue approximation in this chapter because it's just a fantastic learning opportunity that really makes you think about what it means to calculate the area of a function and how to implement that in code.